and share my screen. All right. So can everyone see that okay?
Yes.
Just fine.
All right, great. I will, yeah, these are just like Google Slides too, so I will send out or I guess, Julie, I can just send the link to you and you can email it out in the notes from the meeting if that works well. I can also paste it in the chat.
Either works.
Okay, yep, so my name is Will. I think I know most everyone on here. I am the deputy lead developer of the SunPy project. So these are slides that Nabil, Frage, and I put together, who's also a core contributor and maintainer for the SunPy project, specifically talking about the affiliate package ecosystem that we use with SunPy. Okay. All right, so just to start off with, just wanted to give an overview of kind of what we consider kind of in scope for what we usually refer to as the kind of core SunPy package, or kind of lower. We often distinguish between kind of the SunPy project as a whole and sort of the SunPy Python package itself. Between, we use kind of sort of the uppercase SunPy, uppercase S, uppercase P for the project, lowercase s, lowercase p for the kind of core package. So SunPy core, we say, is we usually think of as containing kind of encompassing three major components. So these are tools for doing data download, tools for particular data structures that we use, and then functionality surrounding coordinate transformations, and particular things like coordinate transformations on images. So for data download, I know we probably, a lot of people are familiar with this FIDO functionality. So FIDO is kind of a unified interface to a lot of different common data providers in solar physics. So this includes things like the JSOC, which located at Stanford, which serves data for the Solar Dynamics Observatory, places like NOAA, the VSO, and then various other FTP servers. And what FIDO does is provide kind of a unified interface to get at all of those data sources by specifying attributes, search attributes on your data, things like time, wavelength, what sort of instrument you want to query from. And it provides kind of infrastructure for, well, not infrastructure, but an entry point for searching different data providers, and it's something that other third-party packages can hook into as well. So the kind of other component of the core package is data containers, and our main, well, our primary and our only two ones are math and for 2D image data. So that often that often boils down to is the 2D image data itself plus the metadata that we get from the FITS header, which allows you to do things like coordinate transformations between the pixel coordinates of your image and the actual world coordinates, say on the sun, or specifying things like the exposure time of your image or what date that image was taken. The other component is time series for time series data. So in the past, this is largely focused on things like the XRS sensor on the GOES satellite for characterizing, say, high energy flare emission. But there's been a renewed focus too on in situ data from instruments like Parker Solar Probe and Solar Orbiter as well. And then the last kind of component is coordinate transformations. So SunPy builds on top of the AstroPy coordinate transformation stack by adding kind of solar specific coordinate systems and then transformations between those coordinate systems. So this little somewhat silly cartoon here shows, if you were looking at a loop structure on the sun, you were looking at it from the perspective of this one particular observatory, you would see, kind of just a top-down view. If you were looking at it from another observatory, you would see it as a side-on view. And by specifying it in these particular solar coordinate transformation systems, we can do those transformations and then lay these coordinates on top of our images. And so SunPy provides the functionality to kind of hook into the infrastructure provided by AstroPy. So notably, what we've aimed to do with SunPy is kind of build on top of, and like many of the packages in the PyHC ecosystem, is to build on top of its existing Python stack, right? We don't want to reinvent. None of us want to reinvent pandas, NumPy, et cetera. And so this is a slide from a keynote presentation given at PyCon in 2017 by a guy named Jake Vanderplas. And so you can see that SunPy, actually, I did not add SunPy here. This was actually on a slide. And just showing things like AstroPy and SunPy, build on top of this existing scientific stack. And so I'm showing this to kind of make the point that, with our affiliate package ecosystem, we want to kind of provide like another layer on top of this existing Python scientific Python stack. So I've rearranged this a little bit in that we build a lot on top of AstroPy, and I know other packages within PyHC do as well. AstroPy provides a lot of core functionality like support for units and time and the coordinate stuff that I was talking about previously. And so what we want to do is kind of extend that. So we, in the same way that we build on top of AstroPy, we want to provide sort of a base for other solar specific packages to build on top of. And so this is the idea behind our affiliated package ecosystem. So this whole affiliated package system is laid out in detail in this thing that we call an SEP, just SunPy enhancement proposal. These are kind of analogous to the Python enhancement proposals. And there's actually, in this presentation, there's a link to that, so you can go and read the kind of nitty-gritty details if you would like. But the idea is that we have these things called sponsored packages and affiliated packages. So we say that these sponsored packages are things that are outside the scope of the core package, and that kind of data download containers and coordinates scope that I laid out before. But there are also things that are kind of core to the project and that are maintained by maintainers of the project. And so these are things like DRMS, which is provides underlying search functionality or for hooking into doing queries against the JSOC. IndieCube, which is a core data structure for doing holding n-dimensional data plus a WCS. And that's becoming a more important, an increasingly important part of our ecosystem. I know others others within the PyHC community have used IndieCube as well. And there's a few others that we'll talk about, in particular SunKit Image and SunKit Instruments, and there's another package called SunKit DEM that provide kind of added functionality, common functionality in solar, provide common functionality in solar physics, but are not part of within the scope of the core package, but are still maintained by maintainers of the SunPy project. The other layer to this are affiliated packages. So these are, we say, curated by the SunPy project, but not necessarily maintained by our community. So these are packages that come from kind of outside the circle of core maintainers, but that want to kind of hook into the SunPy ecosystem and kind of, I guess maybe the best way to say it is kind of things that we endorse in a way, that abide by the kind of standards that we set out that I'll talk about in a second. So these can include instrument packages like AIAPy, which is a package that does provide specific functionality for dealing with data from AIA, or packages that implement particular analysis techniques. And one of these examples is PFSS-Pi, which provides functionality for doing potential field extrapolations. And so what the idea is that these affiliated packages and sponsor packages can take advantage of the templates we provide, and all the support that we provide to these affiliated packages. But in particular, in the case of the affiliated packages, where they're maintained by others in the community, but kind of outside the SunPy project, that the development decisions are made by those particular instrument teams or package maintainers. We're not trying to dictate the kind of nitty-gritty decisions or what goes into their packages necessarily. We're here to provide support for them and things like templates for them, but not dictate what goes into the packages. So I guess this is sort of a preview for my next slide, but with these kind of standards that I've alluded to for these affiliated packages kind of fall into a couple different categories that I'll discuss more on the next slide, but that they implement this sort of stoplight system when it comes to evaluating them against these criteria that we have. So this is very similar to the PyHC package evaluation system as well, and takes, I think both actually take a lot of inspiration from the AstroPy affiliated package ecosystem. So feel free to interrupt me at any time if there's any questions. I mean, I'm happy to take questions at the end, or just jump in and feel free to ask. So these review criteria that I've alluded to for kind of evaluating candidates for our affiliated packages fall into several different categories. So these are, and so I realize this is a lot of text on the left side of this slide. You're not meant to read all this, and I realize it's also very small. Again, there are links to we have a whole page on the SunPy website that provides all of these details and that you can look through. I'll just kind of skim over them. Yeah. So there's several different categories that we use to evaluate these packages, and these include functionality, integration, documentation, testing, duplication, community, and development status. So you can see that for each of these categories, we have kind of generally speaking a red, an orange, or sorry, a green, an orange, or a red category that a package can fall into for each of these categories. And this is depending on how they kind of how they evaluate for this particular category. They're assigned one of these badges. So functionality is just, are they doing something that's relevant to a large cross section of solar physics? Are they implementing something that's specific to some subset of the solar community, or is this package not relevant to solar physics at all, right? In this case, the kind of general or specialized label, we don't say one is better than the other. This is just to give information to users. How in general is this package supposed to be? For integration, this is how well is this package making use of the kind of core functionality that the SunPy core package is providing. Are there things that they could be using that they're are they making use of kind of the package at every place they could? Then we would get a score of green. If there's some places where they're not, then they would get an orange score. And then if they're not making use of the package at all, then that's obviously would be a check against them. Documentation is fairly self-explanatory and is very similar. Documentation and testing both fairly similar to the evaluation for all of the PyHC packages. Are you providing things like doc strings? Is your documentation hosted online? Is there API documentation, for testing? Do you have unit tests? Do you have integration tests? Are you using a testing framework? Are you running on CI? Things like that. Things that I think we're all kind of on the same page about. For duplication is very similar to integration in that we for the our affiliate packages, contributions that are coming from the community, but outside of the SunPy project, we don't want them to be duplicating things that already exist in the core package. We want them to be using these pieces of functionality from the core package. But then, I mean, also the flip side is if they're not using things from the core package, there may be great reasons, and we want to know why, and we want to kind of engage those package developers and find out maybe there's some piece of functionality that we're missing from the core package that could be upstreamed and made more generally useful to the wider community. So there's a give and take there as well. The community aspect is perhaps a bit more fuzzy in a way, in that we don't want people just kind of putting their code out there and then kind of not engaging with the community. We want to have, I mean, and for the reason I just mentioned on the duplication side, we want to have a dialogue with the people that are developing these packages from the larger Solr community, and then also that from more I guess a slightly more quantitative standpoint, for lack of a better words, do they have things like a code of conduct? Are they on GitHub where they can welcome contributions from other people? Are they reviewing pull requests, responding to issues, things like that? And then development status would just be, is there at a bare minimum, is there a released version of the package, and is it like a pre 1.0 or a post 1.0? Like how stable is the API? And so all of this kind of culminates in a score for the given package. So for it to be accepted as an affiliated package, we expect it to have a green score in the functionality, but what that means is just that it's relevant to Solr physics, right? That's the bar that we want for it to be accepted. And that there are also no red scores. So, there's some integration, there is documentation, there is testing, you're not completely duplicating all of SunPy, and that there is some community engagement. And then we also have a provisional status, and I'll go into a little bit more on what that is on the next slide. But that, basically what that means is that as long as it doesn't have a red in the functionality, duplication, or community criteria, and that there's an intention to correct those issues, like say in integration, documentation, testing, and duplication. And then of course the last category is just that it's not accepted, so it's out of scope. The functionality is not appropriate for Solr physics, or there's some package that's completely duplicated our core, the core package, and maybe there are good reasons for that, but it wouldn't be appropriate for an affiliated SunPy affiliated package. So the process for doing this is kind of as follows. So we've laid out that previous slide. I laid out kind of what our criteria are, and we've also laid out a fairly exhaustive process for what a review of an affiliated package looks like. So the first step is that the person who's proposing their affiliated package would open a new issue with an issue template on the repository for our website, for the sunpy.org website. We have an assign role for that. I believe at this point is unfilled, but would be done by one of us as the maintainers. Will identify someone to review the package, someone from the project to review the package who is not who doesn't a developer of that package, so an independent reviewer. They would evaluate the package against all those criteria that I just showed, and would add their reviews as a comment on that issue. So all of this takes place in the open on GitHub on an issue. The author can go through this and say, okay, I'm okay with this, or they can request a re-review. After all this, it's either accepted, given provisional status, or not accepted. So those one of those 3 criteria that I listed on the previous slide, based on all those scores. And if that's accepted or is given provisional status, then we would the author of that would then submit a pull request to the website to then add it to the list of affiliated packages on the sunpi.org website. So again, that process is all done in the open. For existing, so this is for new packages. For existing affiliated packages, our goal is to do a re-review of the existing affiliated packages every year, with the criteria that there's not the score in each of those categories has not decreased, right? So that someone hasn't gone from a green to an orange, and say like their documentation hasn't gotten worse, or their testing hasn't gotten worse, right? Or that these things are still maintained, because we don't want to just have a list of stale packages. That's not useful to anyone. For packages that have been marked provisional, we want to go through and make sure that for these provisional packages that the package authors are striving to improve in those categories that we've identified that need work. So if they only had 20% test coverage and say weren't running on the CI, that they're making steps to kind of improve that. And if not, we want to kind of engage them and see what the status of their package is. So that but the point being that there is we don't just want to let this list of packages that we've curated just sit. We want to make sure that it's up to date and relevant to users who might want to use this as say, I want to what is the relevant set of packages for me to do my analysis on my data set in the context of solar physics. So thus far, I've kind of laid out all this kind of in theory. So what does this look like in practice? So we've established this set of review criteria for our affiliate packages, and we've laid out this workflow. And we've applied this review criteria to all of our sponsored packages. So that includes things like for the core package itself. So we applied this whole review to the SunPy core package, to also things like NDCube, and DRMS that I mentioned before, things that are maintained by the project but are external to the core package, and that all of those have had this criterion applied to them, and that this review applied to them. We've also applied this to 2 affiliated packages. So one of them is AIAPI, which is an instrument affiliated package. It's maintained by the group, the AA instrument team at Lockheed Martin, as well as PFSS-Pi, which is maintained by David Stanby. And so we've run those 2 through this system. And so far, those are the only 2 that we've done, but we want more. We'd like to apply this to more contributions from the solar community. So Nabil, I don't know if you wanted to if you have any comments on this slide, if you wanted to say anything particular about SunKit image.
Yeah, so I guess my view on this slide is, so SunKit image is an example of a sponsored package, but it's technically under our system from the previous slides is provisional, because a lot of the functionality in it is actually designed to work on NumPy arrays. So if you pass it in a map, for example. So it's an example of a work in progress that we're hoping to improve in the future. So we're trying to offer some useful image analysis tools that have been developed from researchers that have published papers. So, for example, the multi-scale Gaussian normalization is from Hugh Morgan, who's in Aberystwyth, who wrote this many years ago. And we decided to port a version into Python. We have a version of like Ash Wanden's coronal loop tracing in the bottom right. And it's kind of the most interesting package, I think, under the affiliated system. It's just that I've done a very bad job of advertising it, and no one seems to know it exists. And we spent quite a bit of time on this, and I'm planning to spend a bit more time on it as well. So I'd like to just throw it out there. So if there's any like algorithms that you would consider that might be useful, please do email me, and I will see about spending some time trying to implement them in Python.
Yeah, I think that the algorithms that have gone into it have largely been motivated by the kind of research needs / interests of some of the us on the project. I know, like in particular, the time lag analysis technique is something that's really useful generally, but it's also really useful for me research-wise, and so I implemented that and put that in there. I think the MGN similarly and the loop tracing as well. But that's, you know, we would like to change that. We don't want it just be a reflection of, you know, the needs of the core contributors. We want this to be a more kind of community-based project. So. Okay, so the last slide, I just wanted to sort of tie this into the kind of obviously the PyHC picture. So my understanding of PyHC is that, right, this is provides a community knowledge base for heliophysics research in Python, and that we've, you know, as evidenced by the standards document that we've had for a while, and that we apply to packages that, you know, want to be associated with PyHC, you know, that these standards are built to kind of foster interoperability between all the packages that we have, and that, you know, the one of the goals is to kind of coordinate the development and assess the common needs across all of the packages, as you know, in particular the core ones like Plasma Pi, PySat, SpacePy, and SunPy. And so I guess the kind of one of the things I wanted to throw out there is that can parts and I guess in a way we've already done this with the package review process, but, you know, can this affiliated package approach be generalized to fit the needs of the PyHC community? You know, what parts can, what parts can't, and I guess my kind of conception of this is just in these few bullet points, and I realize that none of this is new, that we've done versions of this already, but sort of identify the common needs across all of our packages, you know, identify what the gaps are in functionality and where the overlaps are, and maybe try to establish some sort of dependency hierarchy. And by hierarchy, I don't mean like which one is better, which one is not, which one is lesser. That's not what I mean at all. But just in terms of like what like core dependencies, like which packages provide more kind of lower level functionality, which ones provide higher functionality, and is there room for things to depend on each other whereas they might not right now. And then to kind of I guess the kind of almost action item from all that is to coordinate development across packages to kind of to enforce that hierarchy and fill those gaps or reduce those overlaps. So that's all I had, and I'm happy to take any questions if we have time. I know there's also another speaker as well. So thanks.
Yeah, Alexandre was able to join. Does anyone have a quick question or two for Will before we move along? And thanks again, Will, for this great presentation.
Just quickly, I assume there's some place where I can find the list of core packages and affiliated packages and all those lovely things.
Yes, so this, I guess these will be shared out, but this link right here, that sunpi.org/project/affiliated. This you'll be able to click this in the slides, and I can include this in the. Or I can send the link to Julie to include it in the notes as well. But yeah, so this page lists all of our affiliated and sponsored packages, as well as all of this review criteria and all of the kind of stoplight system that we have as well. So this was just this largely was just a summary of that page.
And at some point, I think it would be useful. Well, it may or may not be useful, but I think something like a SPACE description of these things. We have a software resource type, and being able to do searches and discovery on these things without having to dig down into each of these different packages. Having a general registry of capabilities could be a useful thing. It's not trivial. I don't suggest it lightly, but in order to make these things really accessible, I think it's something we could think about.
Yeah, I know we had talked about that in the context of the PyHC criteria as well, which is very similar to this. Yeah.
Great. Well, if anyone else has any questions that they think of later, I'll be sure to include Will's email in the notes for today. Let's see. Alexandre, are you ready to present on SPECY?
Can you hear me?
Yes.
Yes, you can. Okay. If you can just give me a second. Do I have right to share screens?
Should be able to.
Can you see my screen?
Yes.
Yes. So, hi everyone. My name is Alexander Schultz. I work at a lab in Toulouse called IRAP. And I'm here to present SPECY, for Space Physics Made Easy. It's a small Python module that we use to access data from various data providers for space physics. So CDA Web, SSC Web, and AMDA most recently. So it's an open source library that puts an emphasis on trying to have a very user-friendly way to access data and representing all the metadata associated with data sets that we can find on AMDA and CDA Web, etc. And just providing a unified and intuitive way of retrieving the spacecraft data sets. One of its main components is its cache system. So we use it to do a lot of machine learning with at the lab, and avoiding downloading many times the same data set is very important for us. So SPECY kind of provided a solution to that. If I go over a little bit of history about SPECY, initially the package was called SPWC. It was supposed to be a data retrieval tool used by Cyclop, which is a data visualization tool developed in the LPP by Alexis Jandet. So Python was chosen because it's a very user-friendly language. Don't want to use C++ to access and manipulate data. A lot of interns and new doctorate students use a lot of Python nowadays, so it was important to provide a tool for Python. And in parallel, we were developing a package called AMDA-Py that provided access to data sets available on AMDA. And we decided to merge both of these projects into one that is now called SPECY. So most of the data sets that are used with SPECY are time series data, catalogs, and timetables. So they all share a similar structure where you want to retrieve data between a start and an end time. That's why we spent a lot of time to have a unified interface for downloading these datasets, and also providing a bunch of useful tools to explore products available on these various data providers. So this is a bit of history about AMDA and it's merging with the SPISI. I'm sorry, I just got these slides right now. I was prepared to do the presentation a little bit later this week, so I'm a bit unprepared. So I don't know if I should go too much into detail about how SPISI works. Mainly there's one function that's used to access data across all of the dataset providers. You usually get data with the dataset and identifier and start and stop date, with optional parameters to include, for example, resampling the data or other parameters that are accepted by the data providers. And we try to use caching as much as possible. So every time data is downloaded, it's stored either locally or on a proxy server that uses SPISI. And next time data is downloaded, it'll just be retrieved from the cache. So this saves a huge amount of time, especially when dealing with large data sets. The design was also made so that the proxy servers are just instances of SPISI running on a server, and we can kind of create a tree-like structure where different groups in the same lab can share a main proxy point that stores all of the data sets used by the lab, and then individual groups can have their own proxies with their own data sets. And so when retrieving data, instead of just looking at, as you can see in this representation here, initially we just execute the function get data on your local computer. It would query the provider, so AMDA, CDR Web, SSC Web, etc. And then you'd retrieve the data, and the caches improve this workflow immensely. It allows us to download a large number of data sets and work much more easily, especially with everything concerning machine learning. We have a need for a lot of data. So it's really a very small module aimed on being as easy to understand and manipulate by anyone. All of the variables are represented by objects that are called SPISI variables that store the time data and the data, the actual data as NumPy arrays. SPISI indexes are objects that represent the various products that are available in AMDA, CDR Web, etc. And spent a lot of time trying to make the SPISI accept auto-completion. So it allows people using Jupyter notebooks or interactive Python terminals to navigate using tabs. I mean, pressing tab, you can kind of navigate all of the objects that are available in different providers. And then we have dataset, timetables, and catalogs, which are datasets are collections of SPISI variables that share time. Timetables are just a collection of date-time ranges, and catalogs are pretty much a generalization of timetables where we have extra columns. So we can see some examples of we're working actually right now on developing a collection of notebooks that illustrate the use of SPISI. I don't know if read the docs right now. Nope, this is not it. Sorry. Still, well, I can't find the documentation. I'll have to send you the link later, but I think I'm done for my my contribution of today.
Awesome.
Thank
Thanks,
you all.
Alexandre, and apologies for any miscommunication that may have happened.
I'm sorry. It's my fault.
No worries. No worries. If you could send me your slides in an email or a link to them, that would be great.
Of course.
Does anyone have a quick question or two for Alexandre?
Is there a place to go for a quick demo?
I have a couple of demonstrations on my computer if you want.
Sure.
Just
Yeah.
give me an instant. So I'll just start this again now. So, for example, have some, no, this is not it. Still working on providing a bunch of tools to use with Speezy, but that cannot be included inside the actual module. For example, interpolation routines, etc. So this is a notebook that just tries to make the spectral representation of Themis B ion density values between May 2000 for a period of 10 hours on May 16th, 2008. So the parameters are identified on AMDA by a unique identifier. This identifier you can find if you, I don't know if anyone here knows AMDA. AMDA is an online visualization tool for space physics data sets. So every data set in AMDA is uniquely identified by a string that you can find in this AMDA tree. So it's here in this little bubble that just appeared. ID IMF, for example. The data I am plotting here is not ACE, it's Themis, Themis B. Ion density, this is not what this is it. The THB, no, ion density, THB-NI. So that parameter is passed to the Speezy get data function, preceded with the AMDA slash to indicate to Speezy that it should retrieve the data on AMDA and between the dates that are provided. So start and stop can either be dates represented as strings or date time objects. And so this is the plot that we would see in AMDA. And we can retrieve retrieving the data is done here. There's not many data points. And this is the plot that we have on my computer. As I said, most of the data that's available on AMDA are time series data. So I don't have many very interesting plots to show you. It's more of a tool, a very useful tool that we use a lot, but it's not very visually impressive. Nope, that's not it. Go. there. I don't know if you have anything specific in mind that I should show you.
Can you go back to the calling sequence, back to just the basic?
So basically, you have to know what.
Do I end up? Do I end up getting a? What is P? In fact,
What is what?
What do I get? How do I recognize my variables?
Well, that's the problem with AMDA and with CDA Web. You have to know the identifier of the data set you're downloading.
No, that's fine. But then when I load it in, I get a set of variables in some form as part of a NumPy array or part of a.
Yeah. Okay. So here's this is the SPECY product object, SPECY variable, and then you can get the time data in this P time attribute, which is a NumPy array, and as well the data is in the data attribute, which is also a NumPy array. So
Okay.
these
Does it bring its metadata labeling it so I know which data set?
and there's also a metadata attribute.
Okay. And that's going to tell me which of the columns in my NumPy array are particular variables.
Yeah, this has all of the metadata associated with the parameter data set that you're downloading. These are all informations that were included in the CDF files downloaded from CDA. AMDA has a different way of providing data. We manipulate a little bit the CDF files and convert them to netCDF, which is the format in which all data sets are stored in AMDA. We're currently working on moving to CDF. And so through this meta dictionary, you have access to all of the information about the mission, the instrument used, the global start of the data set, the sampling that was used, and etc.
Okay.
They're really the main three attributes you can use for the SPECY variable are just its time, data, and metadata.
Be nice to have metadata linked to something like SPACE.
I'm sorry, I didn't quite understand.
If the metadata can be linked to something like SPACE, then the variables would have more of a description and all that.
Yeah, I'm sure that would be a good idea. Yes.
AMDA has a very SPACE-like dictionary behind it.
AMDA uses SPACE files for its for all of the data sets metadata.
Yeah, so they have it. There's when we talked to them earlier this year, even just a few weeks ago, they said there's just a couple of things they're trying to square away before they publicize the full SPACE access.
Yes.
Okay.
We're
Cool.
trying to bring all of the SPACE files back to the most recent version of SPACE. So it's taking a little bit of time, but it should be done within the next year, I hope. I'm not doing that part of the work in the CDPP.
Yes. What I'm worried about is that when I look at this list, it's hard for me to figure out exactly what I'm going to do to pull out.
It does require a bit of manipulating, and so you can use the auto-completing features of interactive Python terminals or notebooks to navigate what we call an inventory. The inventory contains a data tree for AMDA, but also for other providers. So we have, AMDA, SSC, and there should be CDA Web. The problem with CDA Web is that the amount of data sets provided is huge. And we have a hard time parsing all of this information when SPISI is loaded for the first time, it'll retrieve from AMDA, SSC, and CDA Web the complete inventory, and we'll store it in a local cache. The problem with CDA Web is the inventory is quite huge and it takes a bit of time, so that hasn't been implemented yet. But with AMDA, you can navigate all of the parameters, for example. So they're stored under the common hierarchy mission, followed by instrument, followed by dataset ID and component ID. So ACE, MFI, and you can get ACE IMF all, which is a parameter, and then you can get, ACE IMF all is a data set, and then you can get the individual parameters like this. This object is a SPISI index object, and you can pass it to the get data function to download the data. So insert cell below. There. Now we have another SPISI variable. There's,
Thank you.
Thank you. If there are any other questions?
Sounds like not. I'll make sure to include your email in the notes from today that I send out, which will probably be sent out tomorrow. So if anyone has any more questions to think of later, feel free to send a line to Alexandre. I'll also be presenting on day 5 of our PyHC summer school if you signed up for that. So get excited for that. Let's see. Our next Telecon will be May 9th. We'll have a SciPy, I think is how you say it, PSIPY, project intro, as well as a HelioCloud overview from Brian that was rescheduled from a little bit ago. So I will see you all then. Thanks, everyone.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Yes.
Bye-bye.
Bye.